the goal behind this video is to take some of the complexity and some of the intimidation away from a PID calculation so it's not as confusing. For me, when I looked this up 10 years ago, I was thinking, oh, I'm going to figure this out. We'll see what we're doing here. So I look it up. This is what you see on Wikipedia. Well, I instantly start feeling like an idiot because I have no idea what this symbol means right here. I have no idea how to calculate this. I'm thinking it's like algebra. I'm just taking KP times ET plus KI times whatever that thing is, which ends up being the integral symbol, times ET times DT plus KD times this DET divided by DT. So it was very intimidating. If you break down the variables and you start trying to figure out what they mean, well, UT was a controller output. It's like, well, that's okay. MV is your manipulated variable. So if it's a chill water valve, what's my signal going to it? All right, I get that. Your proportional gain. All right, well, you define what that's going to be, and then you take that times ET, which is your error. So this is your proportional part. And if you compare that to an ASI one, it's proportional gain times your error. So, okay, that's simple enough. Plus this, which is where it was the most confusing to me because I'd never had seen this symbol before because I've never had calculus. So KI is your integral gain. And so that's the same as for the ASI controller. And then it's in an ASI controller, you take it times your error sum, which is your sum over time. So all this means up here, this symbol is saying each time I calculated my PID calculation, I'm going to make note of that error. And then the next time I'm going to make note of that error, I'm going to add all those errors together, and I'm going to take that times my KI, which is my integral gain. So down here, it's just my error sum times integral gain. It makes it a lot simpler than just looking at it and have no idea what this means. This is more of defining what it's generally doing. You're not taking what I was originally thinking. You're not taking this times this times this times this and trying to figure all that out. So this is your integral part. Now we're going to go to the derivative. A lot of times we don't use that in HVAC, but KD is just your derivative gain. And then this DET is what's my error at the present time minus the error before. And then this is each calculation time of the controller. So with the ASI one, you just take derivative gain times EN, which is your current error minus your previous error. So you're taking derivative gain times that. If you look, we're going to use this as our example because this is going to be on an actual controller. We're going to get away from this now. It was just to try to color code it to compare what variables were the same in between the two to make it more understandable. So the variable definitions for ASI controls is output in is your controller output. So here's our controller output. That's going to equal our proportional section, which is proportional gain times our error, plus our integral gain times our error sum. So our sum over time, plus our derivative gain times our current error minus our previous. We won't use this in our formula down below when we actually do the calculation. I'll show you the math, but that won't have an effect on our output because we're not going to use it. So the variable definitions, the proportional gain is your max range divided by throttle. So max range is the max range of that analog output. So if that analog output on an ASI controller, the resolution allows for 255 steps. So the max range is 255. Now you could limit that if you want, but let's say our max range is 255 because we want to be able to go to 100%. Our throttle is what is it going to take to get to full output. So if that's 20 degrees, then our throttling range is going to be 20 degrees. So your proportional gain, once you calculate that, you're going to end up using that in our other parts of the formula because the integral gain is proportional times your integral unit divided by integral time. So that's your integral gain. Your air is, again, that's just your control input minus the control set point. So if our control input value is 60 degrees Fahrenheit, but our set point is 55 degrees Fahrenheit for discharge air, well, then we have a 5-degree air. Our air sum is just our air sum all the other times plus this current one. So all airs plus the current one is our air sum. Our derivative gain, again, is just that proportional part, the max range divided by throttle, times the derivative time divided by derivative unit. And then the En minus 1 of that derivative is just present and previous value of the air. So before we go over an actual example, let's get an idea of what the terms, so each one of these sections is considered a term. So the proportional term, integral term, and derivative term. What are they going to have on the effect of the output? So visually looking at it, if we look at a proportional, what we're looking at here is, here's our room temperature, or in the case of a discharge air, this would be our discharge air. This is our set point. So this black line is our set point. So ET is our air. So at this time, our air is this. So our proportional starts going up. What proportional will end up doing is it's going to get to a steady state. So you can see how it comes up, and then it kind of levels off. So our control output right here kind of mellows out right here, and you're always going to be away from set point. You're just going to get close to it, and the controller is just going to call it good, basically. That is where your integral term comes in, and this was the most confusing part to me. Mainly because it had an integral symbol, and I had no idea what that was. So your air is still, you're still looking at that air, but if you look at this dt, that is the air at that time. So if each one of these yellow columns, let's say that represents 60 seconds. So at the first 60 seconds, I was this far away. The next 60 seconds, I'm this far away. So on and so forth. And it's adding all that together. You're trying to figure out the sum of the airs under this curve. So you're trying to figure out this area, like how far away you are from set point. And then that affects your integral output. So as long as there's an error, the integral is going to keep driving that output until you get to 0. So as in, like, you're at temperature set point. The derivative typically has the opposite effect. So the derivative is looking at this error, and then it looks at your next reading time, and it's like, well, we came down this far. So we're up here. Well, then the derivative is going to start driving your signal down. So it's going to dampen it. So meaning typically it's going to be a negative number because you're getting closer to set point. Now, if your previous error is 75 and now we're at 70, well, now we're minus 5. So that's going to affect based on our gain and everything else. If your temperature went up, well, then that's going to change it. It'll make it more of a positive. But the concepts here are the derivative usually will dampen the signal. It's going to react to how fast and how close you're getting to the error to help slow down what your integral output and your proportional added together were. So for example, on an actual calculation, if we go down, I'm going to say, I'm going to ask, what is my chill water valve signal if the supply air set point is 55 degrees Fahrenheit and the supply air is 60 degrees and an ASI control PID analog output? First things first, the control input, control set point, and throttling range, they all have to be in the same units. So if the control input is 0.01 degrees units, then the control set point, throttling range, etc. are also in 0.01 degree units. So the controller sees 60 degrees Fahrenheit as 6,000 because we're taking 60 times 100 because we're at hundreds of a degree. And 55 would count as 5,500 in the controller. So the parameters are the throttling range, we're going to say is 2,000, which is 20 degrees Fahrenheit. Our max range is 255. Again, that's because there's 255 steps for that analog output. So we're not going to limit it right now. We're going to say that's our max range, and that it will equal 100%. Our calculation time, we're going to say every 60 seconds we'll take a calculation. That'll give time for the valve to open and start having an effect on the temperature. You might find that's too long. We're just going to use this for an example. Our integral unit seconds is going to be the same, and our integral time is 240. What the key here is ASI suggestion is to have an integral weight of 0.1 to 0.33. So the integral weight is just this integral units divided by integral time. I'm going with 0.25, so 60 divided by 240 is 0.25. The derivative time we're going to have at 0, and derivative units at 0, so that way it's not using that as part of the calculation. So the very first thing we got to do is we got to figure out, well, what's our air? So if we're putting out 60 degree air and our set point is 55 degree air, well, we just take 6,000 minus 5,500, which is 60 degrees Fahrenheit minus 55. So our air is 500. So our proportional term is just this proportional part, which is max range divided by throttle. So this is our gain, our proportional gain. And we're going to take that times our air. So times 500. So max range is 255 divided by 2,000. And then we're going to take that times our air. And we'll end up using that same calculation for the other terms. So the integral term and the derivative. So we put that information in the known information in. So 255 divided by 2,000 times 500. So our proportional is 0.1275 times 500. So our proportional effect on this controller, out of 255 steps, the proportional is going to drive our signal to 63.75. That's going to be that part of the proportional term is 63.75. The integral term is calculated based on the sum of the errors. So our error sum equals all the sums of our previous errors plus our current. Well, in our case, we didn't have any other ones. This is our first one. So we're going to say our first error is 500 because it's our first reading. We're 500 off or 5 degrees. So we just plug that stuff in. So this, again, this is where the integral gain is this section right here. And what I'm telling you here is it's max range divided by throttle. So that was your proportional times this integral unit divided by integral time. And this times your error sum, which equals integral gain, which is, again, this, times your error sum. So we put the information in the controller or into the formula. And our integral is 255 divided by 2,000 times 60 divided by 240 seconds times 500. So our integral is 0.1275 times 0.25 times 500. So our integral term is going to drive that controller 15.9375. The derivative term, if you were using it, again, would be this proportional gain times this derivative divided by derivative unit. That would end up being derivative gain times your current error minus your previous error. So it ends up being derivative gain. Once you have that calculated out, it'll every time you do this calculation, your derivative gain will stay the same. But your current error minus your previous will not, obviously. You plug all that stuff in, and you can just go down through the formula and calculate it out. Again, we're not using that part. So our actual control output should be output in equals our proportional plus our integral plus our derivative. So our output is 63.75 plus 15.9375 plus 0. So our actual output should be 79.6875 out of 255. So if you take a calculator and you just let's just take 80 divided by 255, and we're going to take that times 100 to get percentage. So we should be at 31.37% output out of 100%. And that's just based on this one very first error. The key is that the controllers are doing all these calculations in the background. It's nice, at least for me, to understand how the calculation actually works and what effect it's having on the controlled variable.